So now, here we have an op amp. I'm using the LM358, one out of two that are on that integrated circuit. We have it wired as an inverting comparator, and we are using a significant amount of voltage for these components right there. So we got 12 volts right there. I can go up to about 14.6 volts. I designed this for 15 volts. Any case, we have a low input right here. We're close to ground. Half of the supply voltage is where our reference is right there. So if I get above halfway when it comes to the trim pot there, now we got a low output. The blue LED lights up. The main thing is high enough input voltage for our signal is a low output. A low enough voltage for our input signal is a high output. That's why it is inverting. And mostly the resistors that I used there were to protect the LEDs and other circuitry from up to about 14.6 volts. So now we got the LM358. There's two op amps in there. It's a dual op amp. We can leave one op amp floating. I haven't run into problems with that yet, although it's probably better to wire it as a voltage follower that's outputting ground. But any case, we're going to use the one on the left there, output on top, inverting input or minus right below it, and then the non-inverting down there. Important to remember, we also got the one over there, but we're not going to use it. You have to power the integrated circuit right there. A positive supply over there, a negative supply over there. Negative supply is usually ground if you're using a single supply. You can use a dual supply though, where there's actually a positive voltage and a negative voltage in relationship to ground. Ground is halfway in between them, usually right there. So there you can see, that's why you see where there's dual supplies, you see half the voltage, but that's plus minus. So ultimately, it's the same amount of voltage, it's just where the ground goes. So we can work down to 3 volts or up to 32 volts. So now, I showed the power connections right there on the schematic. You may not see that. You may just see the triangle there. Realize you always have to power the integrated circuit. Generally, it'll be the same voltages that you see everywhere else, but not necessarily. So now we're going to move on to our load right here. So we have an indicator when the output is low, the blue LED, and we have an indicator when the output is high, the red LED. I like to do that. Now, we're going to work with almost 15 volts. And so we need to protect these LEDs. And so if we got 15 volts across this red LED and resistor, I want at least about 1.5, 1,500 ohms of resistance protecting the LED. So resistors get hot really quickly as voltage starts rising because more current is flowing through them. So in any case, we're going to take the blue LED, I'll stick it up there, and then the red LED. So the long lead the anode's up on top, short lead the cathode's down on bottom. Anode has to be more positive than the cathode in order for it to light up. So long lead the anode of the red LED I'm going to put to the cathode of the blue LED. And so we have it wired up as you see on the diagram right there. I'll shuffle this over and we'll zoom in a little bit so we can get a closer look. And so blue LEDs are really bright. So we're going to get, probably somewhere about half of the current going through the blue LED as the red LED, because I'm going to use a 1,000 or 3,000 ohm resistor, 3,000 ohm resistor right there. And we have that in there. And then 1,500 ohm resistor for the blue or the red LED. So get at least twice the current because blue LED drops a little bit more. But we do have output limitations. We're going to get somewhere close to twice the current going through the red LED when the output is high versus the blue LED. Hopefully you see that there. We have to connect that to the output. So I'm going to just use this jumper right there. And so I got this looped. I can easily jump over integrated circuits and stuff. And also, you kind of want to keep them pointing down, but you can, spread them out and push them in if you make a jumper like this to kind of make little changes to how far the jump is. And this spot I'm pretty sure is bad in the board, so I'm going to go over one over there. Now we have the output connecting those two LED pads right there. Power is off right now. Power supply is off. Make sure you turn power off before you start wiring up the board. You can unplug the alligator clips as well if you want. So we don't have anything lit up. Probably we get like stray signals in the air and stuff, making it flutter back and forth. Not going to damage anything, but you know, no point having that. And if you don't have a power supply that limits current like this, you may short circuit something while you're wiring things up and you know, cause damage. Now we're going to get to our reference voltage. So here I swapped the positions of the inputs. You always have to pay close attention to that. So always consult the pin layout, and if you buy a kit like this, you'll get the pin layout right on there. So this is what I usually consult when I put the pin in the board, to remind myself where the inverting and non-inverting is. But you can see I got other components where even if like the output works differently for the LM393, it's only a comparator. But otherwise, the pin layout is the same right there. So not the exact same component, but that's a common pin layout, what you see here. Be aware of that. On the schematic though, it's common. Usually people draw it where it's most convenient for the schematic drawing, whether the plus is above the minus or the minus above the plus, but the physical component, the minus is above the plus. You always got to remember that. So we're doing an inverting comparator, which means our reference voltage is going to go to the plus input. So pretty straightforward. Usually I like to take a resistor, so 10K, they're equal value, that's all that matters. So we'll get half of the supply voltage. And you know, we could use like 100K resistors as well, but people typically write down 10K resistors when they just need a resistor, you know, that will just let a little bit of current flow through it, but you'll pass along a voltage. So like if I remove this lower one, we have a pull-up resistor. It's going to keep the positive supply to the input. And if we remove the other one, now we got a low pull-down resistor right here, giving us ground to that input. No current's going to flow, but when we have the two resistors, then current is going to flow. So you know, 10K will keep the current low. It's 20K altogether. But also it'll make sure you get a definite voltage. So it's a commonly used value. Now we have the trim pot. So trim pot is similar to these two resistors, except for there's a wiper. Instead of two resistive elements, there's one resistive element, but there's a wiper that divides that up. So if you set it halfway, this is 10K, then there'll be, you know, it's not an exact 10K, but it's close enough. But you set it halfway, then you'll have about 5K on the high side, about 5K on the low side, and you'll get half of the supply voltage, just like the two 10Ks right there. Even though they got 20K total, that has 10K total. If you set it halfway, both of them, you'll get half of the supply voltage. Pretty straightforward. It's an adjustable voltage divider. And you can also go to one extreme where you'll get the full supply voltage to the input, or the other extreme where you get the you know, no voltage, basically the negative supply voltage to the input, and anything in between. It's an adjustable voltage divider when you wire it with the power supply across both inputs. You could just use it as a variable resistor if you got one supply to one of the end terminals, and then a wiper headed through a load or something. You can do that as well. Just be aware of that if you're not aware of that already. And there we go. We put that to the inverting input because this is our signal and we want an inverted output. Pretty straightforward right there. And that's really about it. So we will come back and you'll see that when I apply power, we're at that 14.6 volt. We got somewhere around 10 milliamps of current when the red LED is lit up. That's not all current going through the red LED. As you get you know, somewhat higher voltages, you start having extra current going through like your voltage dividers and stuff. You have to take that into account if you're just using the power supply to look at how much current is flowing. And there's the blue LED, somewhere around about 6 milliamps of current. So I believe there's about 2 milliamps of current flowing through the rest of the circuitry. So probably 4 milliamps of current going through the blue LED. Remove it. There you can see we got 2 milliamps of current, and that's one way you can check right there. And obviously I miswired it because the LED didn't light up. So If you plug an LED in and it doesn't light up when it's supposed to, good chance you put it in the wrong spot or you put it in backwards. So again, 10, it was saying 10 before, now it's saying 9. I think it might go up a little bit as it warms up or whatever, but it's probably just barely 10 milliamps of current. So if it dips a little bit below, it'll say 9. But there you can see, still, we got about 2 milliamps of current going through the rest of the circuitry. So around 7 to 8 milliamps of current going through the red LED. So that's one way you can kind of test out things with the circuit, looking at how much power the power supply is having to provide to it. It's one simple way that you can do that. Now we have again somewhere about 7 milliamps of current going through the red LED approximately. That same amount of current will go through the resistor right there. So now we're gonna take a quick look at this resistor here. This is the one that's getting the hottest, and the component that's getting the hottest. So we got about 11 volts across it, about 7 milliamps of current flowing through it, which is 0.007. So the reason why we have that much voltage across it, even though we have 14 volts at the supply, 14.6, we're losing over a volt because the output just doesn't provide as much. That's the output voltage right there. It's not providing the full supply voltage. As you can see there, 14.6. Output, you know, especially when you got loads, the more demand that the load has, the more that you're going to lose. So I got the calculator right there. I'll try to keep the glare off it. But in any case, we have basically 11 volts right there times the current in amps right there. So 7 milliamps is the same as 0.007 amps equals, and we saw the result down there. So these resistors are quarter watt resistors. So that's 0.25. This is much less, but you should still stay halfway below that, 0.125. And so this is a bit below half of that right there. So you know, the resistor is going to get warm, not terribly warm or anything. But again, if we use the lower value resistor, we'd have more current, and therefore it would get hot pretty quick right there. So for 15 volt circuits, I generally, remember, we're not getting the full 15 volts out. Actually, we got this set to 14.6. Not getting the full 14.6 volts out, that's helping. But in any case, we have the potential when we're getting up to 15 volts. I think 1,500 ohms is kind of the basic resistance, minimum resistance you want to use in those circuits. Of course, you can always go higher if you need less current or whatever. Perfectly fine. That resistor is going to get about half as hot as this one right there, just because of the lower current. It's going to have about the same amount of voltage on it when it has current flowing through it. So now, that's the demonstration and explanation for the inverting comparator. Main takeaway is high input, low output, and then low input, high output. We just use the LEDs to indicate that. I do that in a lot of my circuits because there's a lot of circuits where it's important to understand when it's going high and low, and you know, it helps if you see color-coded LEDs to help indicate that. Thanks for watching. Make sure you check out one of the other videos I'm posting on the screen, and check out links down below. They all help out a lot. I'll see you in the next video.